Right, fluid review. We're going to be thinking about 5 concepts for this unit. We'll talk about pressure, Pascal's principle, Archimedes' principle, the continuity equation, and Bernoulli's principle to kind of round out this review of this unit. This video might get a little long, so feel free to fast forward or rewind or do whatever you need to do that best suits your review needs. The first one I'd like to talk about is the pressure. When we're thinking about pressure, we can really think about 3 different equations. This first equation is useful to use when we're thinking about applying a pressure more in the solid sense. So if I'm thinking about I'm standing on the ground, how much pressure am I applying to the floor based on the force and the area of my feet that are applying to the ground, we might think about the pressure applied by a box, but we don't really use this equation as frequently when we're talking about liquids, in particular maybe a scuba diver or somebody that's going into a certain depth of water. This first equation is really not as commonly used for those situations. It's more commonly used for for hydraulic lifts. So we'll kind of come back to these hydraulic lifts, but that is more the common time when we see this equation used. The other 2 equations, however, are more commonly used when we're talking about liquids at given depths. And the reason why is because we really care about the density of the liquid, the depth, which is h, that the liquid that we're going down, and then the gravity. In both of these equations, really the area is not important, nor does it really matter. So don't get thrown off if you see a question that asks you for the change, or maybe asks you for the hydrostatic pressure or for the gauge pressure. So this is the hydrostatic pressure, and the equation on the right is the gauge pressure. Don't be thrown off if you see a multiple choice question where you're given the area, but then you're also given some of these other variables, density, height, gravity. The area is not important for either of these equations. All we need to know is the density of the liquid, the gravitational constant, and then the height or the depth that the water's at. And when I talk about liquids, I usually refer to water, but remember, we could be talking about any liquid here. So we may ask for an unknown density, or we might talk about a liquid that has a given density that's not water. But in this video, I might reference water a lot just out of habit. So next, let's talk about Pascal's principle. And really, Pascal's principle is used most commonly when we're talking about hydraulic lift. And a hydraulic lift is really going to be this apparatus where I'm going to be pushing down on this handle on the left, and that's going to actually cause the car to rise on the right-hand side. And possibly this will let me get under the car, maybe change the oil, maybe fix something about the car. And so that's really the purpose of a hydraulic lift, is to be able to physically lift the car and then usually get underneath it. So it's not necessarily like a whole platform like this as much as it might be stands or something for the car, but for right now, imagine that it's a whole platform. When we think about the Pascal's principle, we're going to think of this equation that the force applied in the area 1 divided by the area 1 is going to be equal to force applied in section 2 divided by area 2. And really what's nice about this is we begin to think about the force applied being a very small value, and this very small area. And what that's going to allow to happen is a very large force to lift this car over a larger area. And the most common mistake here that people make is that they usually are given the mass of the car. Let's pretend you're given a mass of like 1,000 kilograms, and you're expected to kind of know what to do next. You're not given a force value, so you're not really, this value's hidden. And you need to know actually that the force that the car applies to the piston itself, to this larger section, is going to be equal to the weight of the car, or the force of gravity of the car. And so by knowing the force of gravity for the car here, so that would be 10,000, 1,000 times 10, then we know that the force upward has to be the same value. And so this would also be 10,000 newtons as a result of the force of gravity that the car applies down. So that's kind of the most common mistake that people make. I think the equation is fairly self-explanatory and pretty comfortable. Archimedes' principle, there's some intense math. Let's talk about this. Really what Archimedes' principle is all about is that the buoyant force of an object, let's pick a beaker really quickly, it doesn't matter where an object is in this beaker, the buoyant force of the block that I throw in this beaker is always, always, always going to be equal to the weight of the water displaced. And we've been throwing that phrase around, weight of the water displaced, but I still think many of us don't quite know what it means. So that's where I want to bring in this other equation. Remember that the weight of the water displaced is going to be equal to the mass of the water, so mass of H2O, times gravity. Now, there's no way that I can take the amount of water that's displaced in these scenarios and throw it on a scale. So I need to break down this equation even more to solve for the mass of the water. And now this is a really, really common problem that we see in a lot of fluid questions. Hint, hint, you'll want to be comfortable with doing this. We need to understand that the density of our liquid in this scenario is equal to, and so I'm going to say density of L for liquid is going to be equal to mass over volume. Volume, not velocity, my dears, volume. Well, let's simplify this equation to solve for M and then plug it in. So I rearrange the equation so that I get now the density of the liquid multiplied by the volume equals the mass. Okay, I can plug that in for M right there. So I get a new equation now for the buoyant force again, still working up here. And we see that we've got the density of the liquid multiplied by the volume is equal to mass time, or I'm sorry, is equal to the gravity. Now you may be asking yourself, wait, what is V equal to? What is V equal to? And V is going to be equal to the volume of the water displaced. The volume of the water displaced. Now this is where the situation gets tricky. Are we talking about a floating object or a sinking object? I'm going to break that down over here. If I'm talking about a floating object, when we think about that volume of the water displaced, we're thinking about the volume of the object that's underwater. So I see over here to the right, I've got a block and a beaker with water, and it's going to be, the volume is going to equal to the volume of the block that's underwater. That's an important concept to understand here, is that's going to be equal to the volume that's underwater. The volume that's on top, that's not going to influence the volume in this scenario. Now, submerged is a whole different story, and submerged or sunk into the bottom are going to be the same situation here. We commonly see these scenarios. We're going to see a beaker, the object is underwater, but it's being held by a string so that we actually have it just kind of submerged, hanging out in the middle of the beaker like this. And in this scenario, the volume is actually going to be equal to the volume of the block. So here, what we see is the volume of the water displaced. So H2O displaced is going to be equal to the volume of the object, I should say. Whereas in this top scenario, that volume of H2O displaced, hopefully you can understand those notations, is just equal to the volume of the water of the object underwater. So I'm going to say V under. So that's kind of an important note when looking over to the left at the buoyancy equation. Now, hopefully your brain has not exploded yet, because we have more to talk about. So this is for always, always, always a situation, whether the object is sinking or floating, we're always going to know that the buoyant force is going to be equal to the weight of the water displaced. So that highlighted equation up there, that's like the granddaddy of them all. But now then we can break that equation down further. And here we see really, this is kind of the equation that we use a lot, and we can see where it came from by thinking about the mass times gravity. Let's take a look at all three of these examples here. And really this is kind of the big idea right here. We've got three different beakers, three different blocks doing separate things. Let's identify the forces acting on them. In this situation, we have force of gravity and we have the buoyant force. And these, in this situation, we can say that the buoyant force is equal to two things. In a floating situation only, the buoyant force will be equal to the weight of the water displaced, or the weight of the liquid displaced. But also, in this situation only, the buoyant force is also equal to the weight of the object. This is the only situation where that statement is true right there. that the buoyant force is equal to the weight of the water displaced, but also equal to the weight of the object. And personally, I would want to be comfortable making these two equations and setting them equal to one another. Maybe define something like density or mass. I want to be comfortable finding different variables within these two equations by setting them equal to one another. Second scenario. Here we have still the force of gravity on our way down. We are going to have buoyant force on the way up, but then we are also going to have the tension. This is a very, very common situation to see and a very common question to see. And the big thing I want you to understand here is that the weight of the object is going to be equal to the force of tension plus the buoyant force. In this situation, if I want to find the buoyant force, it's only going to be equal to the weight of the water displaced. The other thing that it can be equal to, just with some math, would be the force of gravity minus the tension. So that's another way to think about that one. And really, it's not so much the mass of the block that's really influential here if I'm comparing, but the density and the volume that's going to be a big deal for these situations. And remember, most of the time, I'm not even given the mass. I have to rely on the rho equals m over v equation and actually solve it for mass. So rearrange it so that I have mass equals rho times v to solve for other things. So just really be comfortable with plugging that in for mass on a regular basis. Finally, we see a block sitting on the ground or on the bottom of the container. We'll have the force of gravity downward. We will have the normal force because it's making contact with the surface, but then we will also have the buoyant force. Now, a lot of people in my section really wanted to also include like a pressure force from like the water, and understand that pressure is not a force. In everyday terms, people might relate pressure and forces as the same thing, but they're not. Remember that forces are going to be separate from pressure, and they're not the same thing. So pressure is not a force that is acting on this block at the bottom of the container. Don't let yourself think that. But what I can remember and what I can think of is that the force of gravity in this situation is also going to be equal to the buoyant force plus the normal force. And those two values are going to equal out to my force of gravity. Now, something really fun to kind of tickle your brain with is really kind of thinking about what makes an object sink, or what scenarios make an object sink, and what scenarios make an object float. And sorry, I keep going up and down on the screen there. I want to jump to a new slide for a second and then come back. So let's play the game. Will it sink or float? And really the key here is to think about the densities. If the density is greater than the density of the object is greater than the density of the liquid, it's going to sink. If the density of the object is less than the density of the liquid, it's going to float. Now let's jump back and look at this last challenge problem here. I really think this is an intriguing example right here of a scenario in which I've got a beaker and a mass, but it also has this tension value. And thinking about what would happen to the tension in this scenario. So I'm still going to have a force of tension. I'm still going to have a buoyant force. But what happens to the tension in this scenario? And really to think about that, I need to jump back one more slide and think about this scenario on the right-hand side where I said that the volume is really reliant on, let me get like a highlighter maybe. Sorry if you don't like the highlighters, I kind of like them. But the volume of a floating object is going to be equal to the volume of the amount of object that is under the water. And so I think that that little nugget of information would be really helpful for this scenario. And I'm not going to go any further than that because I really want you to kind of think about what happens to the buoyant force, what happens to the tension. Remember, this is still true. F of g is going to be equal to F of t plus FB, because that is a given. This object is sitting still, so that means that the object is in equilibrium. So the sum of the forces has to be equal to 0. I highly recommend that if you want to play around with like buoyancy and just kind of test out some of your questions, Google PhET up here at the top right here. So I think I can write on this. Oh, nope, I can't. So Google this PHET at the top here, and you can click here and it gives you this free interactive simulations. I love this site. Then jump down to physics, go down to buoyancy, run now, maximize, and you can actually play around with a bunch of different objects and kind of investigate like what happens to them. And over on the left hand side here, you can turn on buoyant force and the normal force and gravity, and you can even like find the force values, and you can like hold it here and like put it down there and set it back on land, set it over there, and then throw this box in there. And you can kind of play around with different scenarios for yourself. Also, you can do the buoyancy playground. Hoo-hoo, that sounds like a lot of fun. And you can even play around with multiple objects and see like, okay, so if I change this volume here, what happens again? Oh, that happens? I see. What is about the volume of this one? Oh, that happens? Oh, interesting. Just kind of play around with the scenarios. I think for some people, this really helps kind of solidify some of their concepts and their understandings. And you can kind of change the different like objects that you're going to throw in there and be like, oh, that happens. Well, let me see what the buoyant force is equal to. Turn on the force values. Oh, what is the gravity equal to? Oh, it's down there, anticlimactic. And oh, wow, the normal is different, bigger than the force of the buoyant force. Wow, let me check my math on that one and figure it out. So I find this to be kind of a really intriguing, get that out there, a really intriguing place to kind of experiment and solidify my understanding and my concepts with fluids. Next, I'd like to talk about the continuity equation. And if you haven't figured it out yet, you probably have noticed that I really like playing with these PhET simulations. And I'm going to take us to another one that I think really describes and demonstrates the continuity equation in a nice way. So load, Java load. Loading. Well, it loads. Is it coming? Thinking about it. Okay, so when I get to this one, and this is again just another fluid pressure one, I'm gonna click on the flow section. Let's maximize the screen. Ooh, I love playing with this. Now the main idea with the continuity equation is that in areas that have a larger cross-sectional area, like over here on the left, I see that the velocity of my molecules is slower, and you can physically see that in this example. That's why I love this thing. And then in areas where the cross-sectional area is smaller, we see that the velocity is faster. Now let's make it a little more extreme so that we can kind of really see this in action. Make it small. All right, so we see over here on the left-hand side, we see this backup of molecules, high pressure. We also see them going really super slow, low velocity. Also a large area. Well, that's kind of the continuity equation in a nutshell. Let's jump over. The continuity equation is A1, area 1, multiplied by the velocity 1, is going to be equal to A2 multiplied by the velocity 2. Jump back to our simulation. I can see this in action. I see slow velocity in this large area and high velocity in this small area. Now, here's a little Bernoulli extra with this. Bernoulli's all about pressure. I can see all this buildup of molecules here, high pressure, really trying to get somewhere. On the right-hand side, I see this low pressure. Molecules are moving quick, they're moving, they're free to move all around. I think about this like I'm trying to get on the interstate, maybe on the Beltline. Or even, let's say, like you're just trying to find an exit on the Beltline during rush hour traffic. There's this bottleneck effect on the left-hand side. Everybody wants to exit into the one lane exit, but I have 4 lanes trying to merge. So I see this slowing down, high pressure to get into that lane, really this big bottleneck. Once you get into the exit lane, however, it's smooth sailing. You can move super fast. You're like the only car on the road, so it's nice and easy. Nobody's around you. Nobody's trying to cut you off. Life is good again. So left-hand side, bottleneck, trying to merge, slow, high pressure, this is terrible, big interstate or belt line. Oh, hey, check it out over here, exit lane, woohoo, going fast, not a lot of pressure, feels good. Now, what I like about this simulation is you can actually come up here to the right hand side and you can pull down these speed and pressure gauges to kind of give you an idea and really solidify your views there of like, oh, velocity really big, oh, really small, pressure really big, oh, pressure smaller. Kind of like lets you kind of understand those ideas and even kind of play around with things like what would happen if scenarios. What I really expect you to be able to do on the AP test is just be able to think about that scenario conceptually, but also mathematically, and be able to calculate the velocity or the area in both of these situations. Be able to calculate the area, be able to calculate the velocity here and here. Oops, that should be a 1. And we're going to wrap up our review with a Bernoulli equation talk. Bernoulli seems to be kind of the scariest part, and if you can kind of understand Bernoulli, then I think you're smooth sailing. And this is how I think about Bernoulli. I have a pressure, and that's going to be added to like a potential energy kind of equation for my liquid. Except now I'm going to replace the mass. So potential energy, you can remember PE is equal to mgh. But instead I'm going to replace the m with a density. So I have rho gh. Next, I want to think about a kinetic energy situation. That's 1/2 mv squared. Well, again, I'm going to replace the mass with a rho, so I have 1/2 rho v squared. If you kind of think about it like that, I have a pressure plus some potential plus some kinetic, this equation all of a sudden becomes a lot quicker and easier to derive. And really what we see is it's like this scenario in situation 1 or in area 1 is going to be equal to this situation in area 2 plus area 3 plus area 4. It could go on for as many areas as you had in a situation. Now your equation sheet just says it's equal to a constant because it's an unchanging number. Now I'd like to talk about the situation on the right here because this is a situation that's in your study guide, and I talked about it with a couple students and then we kind of didn't come to a conclusion about the correct answer, but now I've got the correct answer for you. So I want to look at this situation right here. We've got a pipe that's got like this thicker section followed by this thinner section followed by this taller section, however same area as B. So area is the same here for these two, and obviously this section on the right or on the left is much larger. So I love that simulation. So I attempted to make this simulation like look lifelike with this here, with this picture. Now there's a few things we can think about right away. So let's jump back to our smartboard. First, let's use our continuity equation to figure out where the velocity is the greatest. So we know that the area 1 multiplied by the velocity 1 in this large section is going to be equal to the area multiplied by the velocity in this smaller section, which is going to be equal to the area multiplied by the velocity in this even smaller section up here. And the key here and what I really want you to understand is that in B and C, the areas are the same. So we must conclude that the velocity here is equal to the velocity in 2 is equal to the velocity in 3. Why? Because the areas are the same. Now, a few of us were talking about Bernoulli earlier and wanting to relate this concept to the Bernoulli equation up top. And let's talk about why this doesn't quite agree with what might be your gut reaction to the Bernoulli equation. Some of you might be saying, oh, well, it got taller, so potential energy increased, so kinetic energy must decrease, thus you concluding that the velocity goes down. That's incorrect. I apply the continuity equation first, and really what that allows me to do is that allows me to continue to observe that, let me jump back to my PhET simulation, that the pressure in this highest area is going to be the lowest pressure in the scenario. That the pressure down here is going to be like our middle range pressure. And then the pressure over in this slower section will be greatest. Let's throw some more molecules in there. So now let's talk about that equation-wise. I think conceptually we can see that. Low pressure, medium pressure, getting bigger, getting bigger, getting bigger. Boosh, getting very big. Oh, I love playing with this thing. So looking at this equation here, the Bernoulli equation, remember this equation is going to be the same throughout the whole thing. So all of this in area A is going to be equal to the same equation in area B, which is going to be equal to the same equation in area C. And I really don't think you want to watch me like rewrite the same equation 3 times, so I'm not going to. But let's talk about the variables themselves. In A and B, what I've done is I have decreased the area, which increased the velocity. And as a result, the height really was the same. So the height stayed constant. And then that allowed my pressure to change. Now let's think about the B and C range. In the B and C range, the height increased. So this value right here increased. But according to the continuity equation, which is kind of what I checked first, I know that the velocity is going to stay the same. Thus, that allows pressure to decrease. And really, you may be saying, but what if I considered this equation first? What if I thought about Bernoulli first? Well, here's what really, this is where I kind of discovered, like, no, we got to really think about that continuity equation first. Because I'm sitting here thinking, oh, okay, so height's going to go up. This value goes up. So then that means one of these variables, either pressure or velocity, is going to go down. Well, the velocity, why would the velocity go down? Because it's the same area, and but shouldn't the pressure be changing because it's getting higher up? And that's quite honestly what drove me to then look at the PhET simulation and experiment and then do a little further research. And no, I came to the conclusion, was able to find some research that said no. The pressure is going to be the value that goes down because this value is going to stay constant because the area over here was constant. Now, if that just made you go, whoa, what? Don't be afraid to email myself or Mr. Culligan or come in before the test on Monday to ask a few questions or maybe just even watch this little session again because I think that that's a really big deal. Last thing to talk about is going to be like a water tower question. Last thing. All right, so we got this water tower type question, and this is what our lab was really all about. And there's a couple problems that I want to talk about that we discussed with the lab that we need to make sure are debunked before this test. First one, at the top of this container, the velocity is always going to be assumed to be 0. Now, you may be saying, but I mean, I know the water's moving, so I know there is a velocity. Well, this velocity is going to be so much smaller than the velocity of the water coming out of the container through the little hole that we can actually just assume it to be 0 because it's going to be an insignificant value. So all of a sudden, when I'm using my Bernoulli equation over here, I can get rid of the 1/2 mv squared because I have assumed that my velocity is 0. That's the first assumption. The other assumption that we're going to assume right away is going to be about the pressure. The pressure is always going to be equal to the atmospheric pressure, so 1 atm. Now, I read something that really shaped this concept for me. Anytime you have a liquid that's exposed to the atmospheric pressure, or the pressure is going to be 1 atm. So anytime the liquid is exposed to the atmosphere, exposed to the air, the pressure is going to be 1 atm, as long as we're at sea level, of course. Now, when I think about the potential energy part, it really is important for you to kind of consider where you're measuring your height. Are you measuring your height from the water level to the hole? Or are you measuring your height from the water level to the table? Or are you measuring your water level to the floor? Because whichever one you choose, you need to kind of keep consistent in terms of calculating then different variables on the other half of the scenario. So make sure you're keeping those different height values constant. Let's jump over to the other side now, though. So now let's talk about our assumptions as the water exits the hole. And we're going to be thinking about right at the hole. First thing that we're going to assume right at the hole is that the pressure is going to be equal to 1 atm. Now, this concept really threw me for a loop because I was thinking, no, but the water's getting pushed out the hole. Shouldn't the pressure be greater? And no, It's not. The pressure at the hole is 1 atm because it's exposed to the atmosphere. The pressure just inside the hole, around here, can be calculated using the gauge pressure. So around here, that's where I can actually use the hydrostatic pressure equation. So I'm going to say in this area, I'd be looking for the hydrostatic pressure, which would be equal to the pressure of the outside, so the atmospheric pressure. So sometimes that's even written as like PATM because it's the atmospheric pressure times the rho, G, and H, whatever that depth is there to the water level. Now, some of you may be saying, wait, can't I just use the gauge pressure here? No, you can't use the gauge pressure because the gauge pressure gives you a change in pressure, and we would actually, in this situation, want to know, like, what is the pressure at that value? So we're talking about what is the pressure at that value, so you'd already have the atmospheric pressure, plus the pressure at that height or that depth. Now let's think back to our assumptions. So again, considering at the hole, we said that the pressure is going to equal to 1 atm, and the height again is going to be really dependent on where you decided the height would be. So if you decided that at the hole was the 0 point, then that means that the height in that situation could be equal to 0, thus allowing you to cancel out the potential energy side of this equation. Now, what I think is really important to note is when I'm thinking about Bernoulli, there are certain variables that can all of a sudden begin to cancel out. We just concluded that the pressure at the top is actually equal to the pressure at the bottom. Cancels out. We just concluded that the velocity here is going to be equal to 0. Cancel it out. Depending on where you measure your height, you may be able to cancel out this portion of the equation. And all of a sudden, what's really exciting is now I'm considering easy ways to calculate the velocity as the water exits the hole. Maybe I'm calculating the height at which the velocity can exit the hole. Maybe I'm saying that the water level must be at this height in order for the water to exit at a given velocity. But I can make all these assumptions because I was able to cancel out certain variables in the equation. Well, that does it for this video. I'm really excited because I feel like this is a test that many people are going to be really successful on. I'm going to throw up a little multiple choice like formative assessment. Make sure you do that for multiple choice just for the fun of it. I think it's a good thing to just kind of test yourself on what values do you know and what values do you not know. Quick side note, please also make sure that you know how to convert from ATMs to pascals for the pressure. Make sure you know how to convert that, okay? In your head, not relying on a calculator. Okay, so that's it. Talk to you later. Have a great day. Bye.